Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, signal processing, optimization, machine learning, etc. This particular video tutorial is dedicated to one very important algorithm for state estimation of nonlinear systems. The name of this algorithm is extended Kalman filter. Since the extended Kalman filter is not a trivial topic, and in order to make these video tutorials as clear as possible, I decided to separate this video tutorial into two parts. The first part that you're currently watching is dedicated to the problem of deriving the extended Kalman filter. On the other hand, in the second part, I will provide an example and I will present discipline Python codes. I noticed that some students or viewers of this channel tend to skip mathematical derivations and immediately start with examples and Python codes. However, this is a bad practice. You will not be able to understand and to properly implement the extended Kalman filter by skipping mathematical derivations. In fact, mathematical derivations are not very hard and they can provide you very good insights into the structure of this filter and into the physical behavior of this filter. Consequently, my advice is to first watch the first part of this video tutorial and then watch the second part of this video tutorial that will be focused on examples and on the Python codes. But before I start, I would like to mention the following. It took me a significant amount of time, energy and planning to create this video tutorial, and consequently I kindly ask you to press the like and subscribe buttons. Thank you very much. Before watching this video tutorial on nonlinear Kalman filtering, it's a very good idea that you become familiar and that you learn the basics of linear Kalman filtering. To make your life easier, I prepared several tutorials that cover the basics of linear Kalman filtering. Links to these tutorials are given over here, and these links are also provided in the description below this video. The first step is to get yourself familiar with the recursive least squares method. You can click over here and you can read this tutorial covering the recursive least squares method. The main motivation for studying the recursive least squares method is that this method is the backbone of Kalman filtering as well as the backbone of adaptive filtering. Consequently, it's very good investment in your knowledge and in yourself to learn this very important algorithm. Once you understand the basics of the recursive least squares method, in this tutorial over here, you can learn how to implement the recursive least squares method in Python. Then, you can read this tutorial to learn how to propagate the means and the covariance matrices of dynamical systems. This is a very important step in understanding the Kalman filter. Then, in this tutorial over here, you can actually learn how to derive the Kalman filter by using the recursive least squares method. And finally, in this video tutorial, you can learn how to implement the linear Kalman filter in Python. Under the assumption that you have at least basic understanding of linear Kalman filters and linear Kalman filtering, we can start with extended Kalman filter. The extended Kalman filter is a generalization of the linear Kalman filter for nonlinear dynamical systems. Over here, we have a nonlinear dynamical system in a fairly general form. The index k of the functions and vectors corresponds to the discrete time instance. That is, we look at the system behavior as well as time signals at the discrete time instance denoted by 0, delta t, 2 delta t, and in the general case, k delta t, and this index can go up to infinity. The vector xk is the n-dimensional state vector at the discrete time instant k. That is, this vector corresponds to the system state at the discrete time instance. Then, another important vector is the input vector uk minus 1 or uk. Then we have the disturbance vector dk minus 1 or dk. This vector is also called the process noise vector. Then we have the measurement noise vector denoted by qk, and finally we have the output vector or the observation vector. Beside these vectors, we also have two nonlinear functions. The first nonlinear function is fk minus 1. This is a nonlinear vector function of vector argument, and the second function is gk. The function gk is a nonlinear vector function of vector argument. The function fk minus 1 quantifies the state dynamics of the system, and the function gk is our measurement model. Before we explain how to derive the extended Kalman filter, it's very important to introduce the concepts of the a priori state estimate and the a posteriori state estimate. The a priori state estimate of the state vector xk is obtained implicitly on the basis of the output vector measurements y1 until yk minus 1. And of course, there is some additional information necessary to compute this state estimate that will be explained later. That is, the a priori state estimate is obtained on the basis of the past measurements up to the current discrete time instant k, and not on the basis of the measurement yk at the discrete time instant k. The a priori state estimate is denoted like this. And let's explain this notation. X is the notation for state, k is the notation for the discrete time instant, hat is the notation for the state estimate, and this minus sign is very important. This minus sign, it means that this is actually the a priori state estimate. A priori, that is before the time instant k. To summarize, the minus sign means that this estimate is computed by using the information obtained before the discrete time instant k. In contrast to the a priori state estimate, the a posteriori state estimate is obtained implicitly on the basis of the measurements y1, y2, yk minus 1, and here's the difference. We also take into account the measurement at the time instant k. The a posteriori state estimate has this notation. Here again, x is the state, k is the discrete time instant, hat denotes that this is actually an estimate, and plus is a symbol denoting that this is the a posteriori state estimate. That is, we take all the measurements starting from y0 until yk and including yk in order to compute the a posteriori state estimate. Another concept that is important for understanding and implementing the extended Kalman filter is the concept of covariance matrices of the estimation error. The a priori covariance matrix of the state estimation error is defined by this equation. On the other hand, the a posteriori covariance matrix of the state estimation error is denoted by this equation. So what's the physical meaning of these two equations? Well, over here we can see that this quantity is nothing less than the estimation error. But this is actually the a priori estimation error, since we take into account the a priori state estimate. And this whole quantity is nothing less than the covariance matrix, and the covariance matrices are quantifying the uncertainty about the state estimation error. Similarly, we define the a posteriori covariance matrix. In fact, as I explained in my previous video tutorials on linear Kalman filtering, whose links you can find in the description below this video, the linear Kalman filter actually minimizes the sum of traces of the covariance matrices for different time instants. That is, in some sense, this is a minimum variance filter. Or better to say, the Kalman filter is the minimum variance filter. Finally, we are ready to derive the extended Kalman filter. We start from the nonlinear state equation. Let us assume at the discrete time instant k-1, the a posteriori estimate x hat k-1 plus is available. Also, let us assume that the value of input uk-1 that's equal to uk-1 star is also known at this time instant. This is a very reasonable assumption since our control algorithm can pre-compute the value of the input at the time instant k-1. The derivation of the extended Kalman filter is based on three main ideas. The first main idea is to linearize the state equation around the a posteriori estimate at the time instant k-1. That is, we linearize the dynamics around the vector x hat k-1 plus. Here's how the linearization procedure works in practice. We start from the nonlinear equation and we use the Taylor series expansion to linearize the dynamics. While linearizing the dynamics, we only keep the first order terms. And as the result, we obtain this equation. Over here, the matrix 8k-1 is the Jacobian matrix of this function. And we will provide the structure of this Jacobian matrix later on in this video tutorial. After rearranging the terms, we obtain the second form of this equation, and finally we obtain the third form of this equation. This vector sk-1 is actually equal to this part over here. What is important to observe over here that at the time instant k-1, ak-1, and sk-1 are perfectly known. This is because we know the a posteriori state estimate and we know the input. And we can linearize the dynamics, that is, we can compute this Jacobian matrix, and consequently this vector is perfectly known. As mentioned previously, the matrix ak-1 is obtained by linearizing the nonlinear dynamics around xk-1 plus hat and around this control input. In fact, this control input is not used for linearization, it's simply substituted in the expression of partial derivatives. More precisely, the matrix ak-1 is denoted like this. This is a standard notation in vector calculus. Here we are saying that this matrix is Jacobian matrix of the vector function fk-1. This vertical bar means that we are computing the Jacobian for this fixed value of xk-1 and for this fixed value for the vector uk-1. This matrix is the Jacobian matrix of the function fk-1 evaluated at these two quantities. Here is the structure of the Jacobian matrix. Next, we will explain the structure and how to compute the Jacobian matrix. This is very important for proper implementation of the extended Kalman filter. In my next video, that is in the second part of this video tutorial, I will explain how to implement the extended Kalman filter in Python. First, let us expand the vector function xk-1. The vector function fk-1 consists of these entries. Similarly, let us expand the vector xk minus 1. Its entries are given over here. The Jacobian is constructed like this. We take this scalar function. When I say scalar, I mean that this function takes a vector argument, that is, it takes xk minus 1, uk minus 1, and it produces a scalar. We take this scalar function and we first compute the partial derivative of this scalar function with respect to the first entry of our vector xk minus 1. Then we take again this function and we compute the partial derivative of that function with respect to the second entry. And we repeat this procedure until the end. That is, until we compute the partial derivative of this function with respect to the last entry of our vector xn. We construct the second row in a similar manner. We take the second entry, or better to say the second scalar entry of our function fk minus 1, and we compute the partial derivatives of this function starting from x1k minus 1, that is this term, then we take x2k minus 1, this term, until the last term over here. And we repeat this procedure for all n entries of this vector function. And in this manner, we construct the Jacobian matrix. Another important vector is this vector over here. This vector is perfectly known at the time instant k minus 1, and here, for clarity, we repeat this vector. This was the first idea of the extended Kalman filter. To summarize, the first idea is to linearize our nonlinear dynamics around the a posteriori estimate at the time instant k minus 1. As the result, we obtained this linear equation. Let us proceed with the second main idea of the extended Kalman filter. The second main idea is to linearize the output equation around the known value of the a priori state estimate xk hat with a minus superscript. Here is one very important comment. At the time instant k minus 1, we know xk minus 1 plus hat. Then, since we know the dynamics of the system, I will explain later on that we can easily compute xk minus hat. That is, we can compute the a priori state estimate before the time instant k. That's why we can safely assume that we can linearize our output equation around the a priori state estimate for the time instant k. That's denoted like this. Again, by using the Taylor series expansion and by keeping only the first order terms, we obtain this equation. We can rearrange this equation to obtain the second form of this equation. And here it's very important to emphasize that ck is actually the Jacobian matrix of our function gk. Finally, by grouping these two vectors in a single vector called bk, we can obtain the linearized output equation. And here it's very important to emphasize that the vector bk is perfectly known before the time instant k. The matrix ck is obtained by linearizing the nonlinear output equation around the a priori state estimate for the time instant k. It's computed by using this formula. Again, we can expand and show the structure of the Jacobian matrix. The structure of the Jacobian matrix is given by the equation number 15. Another important quantity that we need to explain is this vector bk. This vector bk is defined by this equation, And this vector is perfectly known before the time instant k. Let us now summarize the linearized state and output equations. Here they are. This is the state equation, and this is the output equation. The third main idea of the extended Kalman filter is to apply the linear Kalman filter to these two equations. However, we slightly diverge from the application of the linear Kalman filter by actually using the nonlinear state equation of our original system to propagate the state estimates over time. This will be explained in the sequel. Since I want to keep this video as short as possible, I will not rederive the main equations of the linear Kalman filter. I assume that you're familiar with these equations, and I will simply apply them to our problem. That is, I will apply the linear Kalman filter equations to these two equations. And consequently, I derive the extended Kalman filter that's actually summarized over here. So here is the summary. We start from the time instant k is equal to 0. At this time instant, we select an initial a posteriori estimate, denoted like this, and we select the initial a posteriori covariance matrix of the estimation error that's denoted like this. Then, for the time steps, k is equal to 1, 2, 3, etc., we perform the following two steps. The first step is performed after the time step k minus 1 and before the time step k. That is, between these two time steps. So immediately after the time step k minus 1, we perform the step number 1. At this time step, we know the a posteriori estimate, x k minus 1 plus, and the a posteriori covariance matrix, p k minus 1 plus. Then, we first linearize our nonlinear dynamics. That is, we obtain our matrix ak minus 1. After we obtain this matrix ak minus 1, we simply propagate the dynamics of our system. That is, we propagate the state and the covariance equations. Here's how we propagate these two quantities. We take xk minus 1 plus hat, we plug this value in our state equation, and watch over here that this is a nonlinear state equation, to obtain the a priori state estimate for this time instant k. That is, we obtain x k minus hat. Then we take our a posteriori covariance matrix and we propagate this a posteriori covariance matrix through our dynamics for the covariance matrix. As the result, we obtain the a priori covariance matrix for the time step k. We should keep in mind that these computations are happening before the time instant k. And this is very important to keep in mind. And at the end of this time step, we compute the Jacobian matrix of the output equation. That is, we compute ck. Here I forgot to mention that qk minus 1 is the covariance matrix of the process noise or of the disturbance vector at the time instant k minus 1. And this quantity is completely known. Next, let's explain the step number 2. This step is obtained immediately after the time step k. That is, over here. At the time step k, the measurement yk arrives. We can collect this measurement by using a sensor. For example, Immediately after the time step k, we compute the Kalman gain matrix given by this equation. Rk is the covariance matrix of the measurement noise. Ck is the Jacobian matrix of the output equation. Pk minus Pk with the superscript minus is the a priori covariance matrix. And by knowing these quantities, we can compute Kk. That is, we can compute the Kalman gain matrix. Then, we can compute the a posteriori state estimate. We use this equation to compute the a posteriori state estimate. We simply take the a priori state estimate, that is this quantity, we take our Kalman filter gain, we take the output, and we take the nonlinear output equation. By using these quantities, we can compute xk plus hat. That is, we can compute the a posteriori state estimate. We still need to update our a priori covariance matrix. We can update this matrix, that is, we can compute the a posteriori covariance matrix by either using this equation or this equation. The equation 25 is more preferable from numerical stability perspective, and consequently my advice is to use this form. By using the equation 25 and by using the values of kk, ck, pk minus and rk, we can simply compute pk plus. That is, we can compute the a posteriori covariance matrix. This computation process is summarized by this graph. Here we are at the beginning, at the discrete time instant k minus 1, or better to say immediately after this discrete time instant. We have the a posteriori estimate and covariance matrix. At the time instant k minus 1, we propagate these values through the dynamics of the system. Then we obtain the a priori state and covariance matrix before the time instant k. Then the measurement comes in. Immediately after the time instant k, we update our state and the covariance matrix. That is, we compute the a posteriori estimates and we repeat this procedure recursively. Okay, this will be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.